So, without further ado, today's presentation, as you can see on your screens, hopefully, is the dangers of cargo liquefaction to ships. It's going to be given by Simon Mackay of ABL. A little bit about Simon. Simon is a chartered naval architect through RINA and is a senior naval architect with ABL. He was awarded an M.Eng degree in naval architecture and small craft engineering from the Universities of Glasgow and Strathclyde in 2007, before joining Babcock Forsyth on the graduate training scheme. He completed 4 years working in the shipyard, both on refit projects and design tasks, before moving to Brooks Bell in 2011. Here, he was initially involved in stability upgrade projects for RoPax vessels, primarily in accordance with the Stockholm Agreement regulation, before becoming more involved in marine claim and salvage wreck removal cases. In 2023, he joined ABL, continuing this work to provide forensic engineering analysis of marine claims and naval architecture advice for ongoing casualty cases. Simon will give his presentation and will respond to any questions at the end. So without further ado, I'm going to swap seats with Simon, who's now going to give us his presentation.
Thank you, Keith. Thanks for the introduction and welcome everyone to the ABL office. Like Keith said, the presentation is on the dangers of cargo liquefaction to ships. Just a summary of the topics we're going to cover. What is cargo liquefaction? Some of you may know, some of you may not know. Some statistics around incidents and casualties. What are the hazards of a liquefied cargo? The regulations that are in place to try and prevent incidents happening. Some of the aspects of a bulk carrier design, this type of ship that carries these cargoes, and potential design mitigations for conclusions. First of all, what is cargo liquefaction? So, cargo liquefaction phenomenon arises in solid cargoes that are loaded into bulk carriers. So a solid bulk cargo is a cargo that is loaded directly into the hold of the ship. It's not containerized in any way. So generally it consists of particles or granules that are uniform in composition. And as I say, they're loaded directly into the hold. So there's no kind of bags or containerization. They tend to be sort of mined minerals as a common bulk cargo. And one type of cargo that's not covered in this is grain. So grains have their own separate rules and regulations for grain cargoes that must be followed for bulk cargoes. So for liquefied cargoes, what happens is the cargo that's loaded, which is generally bulk, is dry. When it's loaded, it contains sufficient moisture to then become act like a fluid during the voyage, so it might flow and move around the hold rather than staying solid, which is the assumption that's taken from during the design. Due to the motions of the ship, so when it's loaded, it may look fine, but due to the motions of the ship and the wave actions or vibrations, then it compacts, and then that's when liquefaction may occur. Some of the cargoes that are susceptible to liquefaction, so say the granular bulk cargoes, fine particles, or clay-like materials, which are sort of very fine in their composition. These are classed as Group A cargoes under the International Maritime Solid Bulk Cargoes Code, the ISMSBC code, which covers the regulations for these cargoes. So a bit more details on the process of cargo liquefaction. I'm not a cargo scientist or an expert in soil mechanics, so it's quite high level. And the top image that shows the left hand is the sort of a pictorial representation of the cargo as it's loaded with the particles and then some moisture around it. You'll see the particles in contact with each other, so there is resistance to movement relative to one another. However, after the compaction, that contact's lost, so there's that shear strength or frictional resistance is lost. So then that's when it then behaves more like a fluid rather than a solid. Second type is for very fine material in the lower image. So it's a different sort of failure mechanism, but the consequences are the same. So it's a fatigue type failure. So after a number of cycles of the ship rolling, that cargo stability then fails, and then you get shifting or moving cargo. There is another type of failure which is very similar to cargo liquefaction, but it is classed as a different failure. It's dynamic separation. So again, it happens due to the compaction of the cargo under vibrations, whether that's from ship motions or vibrations of the engine, where the cargo compacts and then the liquid rises to the surface. Moisture in the cargo rises to the surface, so you get that separation of the cargo and the moisture. And then obviously sloshing of water happens on top of the cargo. So I have a couple of videos here, hopefully those will work. So this one shows a cargo of liquefied, a cargo of nickel ore that's liquefied. Nickel ore has been referred to as the world's most dangerous cargo. Between October and December 2010, there was 3 ships lost. So in less than 40 days, 3 ships were lost with the loss of 44 crew members. So what you see here is the whole stow is essentially moving with the rolling of the ship. There's 8,000 tons of cargo in this hold. And as the ship rolls from side to side, the cargo moves. And you get that huge amount of kinetic energy as the cargo then comes back and hits the ship's side with a subsequent roll. There's about 500 mil so gap opening up at the side shell with each roll. That one, the next video. So this is a video showing liquefied chrome concentrate, so a different cargo. And you'll see the water sloshing on the surface. So this cargo was loaded and left untrimmed. That means the cargo was essentially left in a big heap in the cargo hold. And within hours of sailing, it all flattened out, and the moisture had risen to the surface. The sloshing water caused damage to the boundaries of this hold, and flooded into the adjacent void spaces. So this just gives an idea of some of the potential risks. So in terms of the sort of statistics around liquefaction cases, so this is an excerpt from a report by Intercargo, which looked at casualties over an 11-year period between 2013 and 2022. The things to sort of pick out from this are, of the 26 ships that were lost in that period, 5 of them were lost to cargo liquefaction, top row of this table. So that's 20% of the ships approximately. Grounding was 12 of the 26, so nearly half of them. But then if you look at the number of losses of life, cargo liquefaction has 70 of the 104. So 2/3 approximately of the loss of life were associated with cargo liquefaction, whereas the remainder causes were far less more deadly. So I guess the points to draw from this that cargo liquefaction is maybe not that common an incident, but when it does happen, it can be extremely deadly to the crew that are on board. This just shows a list of some of the cases. So previously I said there was 3 ships that were lost in 40 days, so that's the top 3 in this table, with a loss of 44 crew members. You'll notice they're all nickel ore cargoes and they're all from Indonesia. There will have been other sort of liquefaction incidents, but didn't potentially lead to the loss of the ship or loss of life, so they wouldn't have been covered in this report. But some of the ones, just to point out there, so the Harita bauxite, so that was loading its cargo in Indonesia. At the time, there was a number of other cargoes that were presented for loading, but were rejected because they were too wet. So the masters of the ships did not accept to load the cargo at that time. The Trans Summer, so from August 2013, that's one that you see there was no lives lost in that. The master in that case actually diverted because of bad weather, and it was anchor off of mainland China, I think, when the incident happened, and it capsized. So it was relatively close to rescue, which is why it was, all the crew were recovered. And then the bulk Jupiter, so you'll notice all of them have a nickel ore cargo apart from bulk Jupiter, 3rd from the bottom. That has bauxite as its cargo, loaded in Malaysia. At the time of loading, there was again heavy and prolonged rain, so the cargo would have been wet. And bauxite at that time was classified, the cargo type was not classified one that could potentially liquefy. So subsequent to that incident, a new cargo classification was made for bauxite fines, which is a cargo that type that may liquefy. So as a sort of outcome of that incident, the regulation. These photos are from the Trans Summer, the one I mentioned that was anchored off of mainland China when it happened. So initially, the vessel reported that it took on a 10-degree list of port, and it was slowly increasing. So they called shore. The management company advised to put some water ballast to try and correct that list. There was a mix-up. Instead of putting water ballast in the double bottom tanks, they put it in the topside tanks. The list kept increasing, and then eventually the master orders abandoned ship. So that sequence all happened within the space of an hour. So it just shows how quickly things can progress. So the first picture on the left shows that the vessel, so 45 degrees or so, has got all the hatch covers closed. And then it goes over and subsequently capsizes. It's slightly unusual to have photos of an incident like this happening. Again, I think that's because it was anchored so close to shore that there was people at hand to respond immediately. So after seeing those photos and videos, just a summary of what are the hazards to the ships of liquefied cargo. It kind of falls under 2 main topics, either stability risks or hazards to the structural strength of the bulkheads and side shell. So from stability, from a worst case perspective, you may say, you think, well, a solid cargo turns to full liquid cargo, so therefore you have full free surface effect, acting in one or more holds, up to potentially all the holds, which ships are not designed to withstand. Or a partially liquid cargo, where the cargo kind of flows around, not as a liquid as such, but kind of as a viscous flowing material, or the sliding cargo where it moves from one side to another and maybe becomes asymmetric in the loading, causing issues with a non-zero heel. From a strength perspective, you see there the static load, static hydrostatic pressure on the bulkheads and side shell that the cargo holds are not designed for. Obviously, during the design stage, bulk carriers are designed to withstand certain loads, but if this is outside that kind of design, the design statement for the ship, so that could become an issue, or the impact load, as we saw in one of the previous videos, where the water or the cargo moving around, just that impact load causes damage to the structure, which then breaches watertight integrity and the consequences that may have. So if we look at the effect of free surface in a bulk carrier, so this is the GZ curve, an example GZ curve from a 5-hole bulk carrier. A kind of standard condition with all holds full of cargo, but assumed to be solid, as you would expect. It's got a reasonable GM value, so it's an area under the curve, so you could say that's quite a reasonably safe condition. But then as you go through and you assume one hold is fully liquid, you can see the sort of stability characteristics reduced, so you get a reduced GM value, and also the whole GZ moves down slightly. And then as you go on, potentially 3 holds liquefied, you can see the difference of the first one to the one on the left and the one on the right. That's a significant difference. You can see where the potential issues for loss of stability come from. Again, this is a worst case example from one regard, assuming that all the cargo is now fully liquid. Another potential issue for stability is the cargo sliding. So this sequence shows the heat cargo in the hold. It's being left untrimmed, so it's in a heap rather than kind of being spread out. So it's not a true liquid as such, but it is able to move under the action of the ship. So if we go through this sequence, so due to the rolling of the ship, the cargo may move to one side and then kind of settle with an asymmetric load. So then the ship has a non-zero heel. Depending on the characteristics of the ship and the cargo, this could be up to 20 degrees or so. Potentially, this may have consequences for the operation of the ship. Not just the crew physically moving around the ship, but machinery may start to have issues working if the oil levels, for instance, drop too low. So you may then think, okay, well, that's the case, then we'll ballast on the other side to bring her back upright, as happened trans-summer case that I showed earlier. So that then brings it back upright. So the cargo is off to one side and the ballast water is off the other side to counterbalance each other. However, this is then potentially another even riskier situation, because we know the cargo has a potential to move, is already moved. So then, under the action of the ship, it may move to the other side, the side which you've got the water ballast on, so they end up have an even worse situation, which then brings the consequences. So you could be submerging down flooding points and all sorts of issues. So it's to do any kind of ballasting operations when you have a liquefied cargo or a suspected liquefied cargo is a very risky option. From a structural perspective, I was saying earlier, it's when the cargo liquefies, it then becomes kind of a dense, viscous liquid. So this figure shows the assumed pressures acting on the boundaries of the cargo hold. For a dry cargo, you get a relatively low hydrostatic pressure on the side shell of the bulkheads. Obviously, the pressure acting on the bottom is the same weight of cargo. And then as it becomes liquid, that hydrostatic pressure increases. It can be 2 or 3 times greater. So the design of bulk carriers in the class rules do not take account of the liquid cargo unless there is certain circumstances where, for instance, the middle hold of a bulk carrier is classified to take ballast water, so it will be designed for that case. But generally speaking, the holds are not designed for this. So in terms of the regulations that surround the carriage of bulk cargo, they are contained in the IMSBC code, the International Maritime Solar Cargoes Code. So it's a mandatory code for bulk carriers. It was became mandatory under SOLAS in 2011, and it contains guidance and recommendations for the safe storage and shipment of solar bulk cargoes. It's constantly under review and updates. As we saw for the case of the bauxite cargo, after that incident, a new cargo classification was made. So yeah, it's constantly under review. I guess one of the main points in the IMSBC code is the classification of cargoes. So there's 3 groups: Group A, B, C. Group A is a cargo that has a potential to liquefy if it has a moisture content in excess of a certified defined transportable moisture limit. So that's the ones, Group A cargoes are the ones that are have the potential to liquefy and cause the issues that we're discussing here. Group B cargoes, they have a chemical hazard, and then Group C cargoes are neither Group A or Group B, so they're kind of the ones that don't have so much risk. And just a note, as I said earlier, this code does not cover grains. The carriage of grain has its own code, the International Grain Code. So within the IMSBC code, it gives a whole list of information, guidelines, recommendations for the carriage of different cargoes. And then there is detailed specifications for each of the defined cargoes. So they have what's called a bulk cargo shipping name, BCNS. That is a specified name that should be provided to the master of the ship, which he can then refer to the code and just check what precautions need to be taken for that. For each different type of cargo, there'll be what's called a schedule, and that will contain specifics around the characteristics of the cargo, any information for specific storage or carriage to do with that specific cargo, and then emergency procedures as well covered in that. So for Group A cargoes, the ones that may liquefy, they need to be checked that the transportable moisture limit will be defined, so the TML, and that the specific cargo needs to be checked to make sure the moisture level of that cargo is less than that defined limit. So that's the limits that's considered safe for carriage. That TML is defined defined by a competent authority, and it's it's basically 90% of the flow moisture point. So within the code, there's procedures to work out the flow moisture point for different cargoes. And then you take 90% of that, and that's the limit transportable moisture limit for that cargo. And then when the cargo is presented for carriage, there will be a certificate to declare the moisture content of that cargo, and that needs to be compared to the TML. So that all that documentation should be provided by the shipper, so that the master is able to verify it for loading. So this is a video that shows you give some signs of what a wet cargo. If you look at the bulkheads or the sides of this, you can see the splatter marks. That's a classic indication of this is a wet cargo, and then you can see as they drop it as well, that definitely doesn't look like dry bulk cargo. So yeah, there's some signs for the crew that there's potentially an issue with this cargo. Ideally, you want to identify that before you load it, because now it's in the ship, so what do you do with it? In this case, you can see there's grabs here, but there is load ports where they load by conveyor belt. There is no discharge facilities. So I have had cases before where the wet cargo has been on board the ship and there's no way to discharge it at that port. So it has to be carefully moved somewhere to be discharged. So if the master does, or the crew do, have any suspicions, there is what's called a CAN test. This again is in the code. This is like a simplified check that they can do just to confirm whether they think any further official testing needs to be taking place for the cargo. So you can see on the right there's a picture of the stockpile, so that's the cargo that's due to be loaded, but it's covered in tarpaulins. But is that effective to keep the moisture out? And you can see it's sitting in a pool of water. So again, there's signs that there's potential issues here. So to do the CAN test, you essentially put some of this cargo in a can and knock it on the desk or knock it on the ground 25 times, I think, and just check if the appearance of the cargo shows signs of having liquid and moisture in it. If there is, then that's when you can say further assessments before loading it. So in terms of the design of the ships that carry these cargoes, the bulk carriers, what potentially is an issue, this just shows an overview of a typical bulk carrier, 5-hold bulk carrier. So the holds obviously span the flow with the ship from side shell to side shell. There's big hatch covers to allow good access to the whole hold. So you can get a crane or a grab in to get whatever's in the hold. And they're generally designed to be as flexible as possible, because they don't only carry bulk cargoes, they're sort of workhorses of the sea. They carry anything and everything. They make up about 40% of the world's tonnage. So yeah, there's a lot of these ships around, and they are designed to be extremely flexible. This just shows a couple of sort of sectional views of the hold themselves. As I was saying, the holds cover the full width of the ship. There's water ballast tanks below, or fuel oil tanks below potentially, and up in the top side as well. Single skin, so that there is only a single thickness of steel between the outside sea and whatever's in the hold. So during the design of these bulk carriers, some of the assumptions that are made, they're obviously built to classification society rules, which again have some implicit assumptions about how they're going to operate, what cargoes they're going to hold. they're not necessarily liquid cargoes. And what kind of loadings are expected to be seen on the bulkheads and the side shell. As I said previously, that there is class rules specifically for holds that do or can contain liquids, generally the middle hold. But they are not applicable generally for the full ship. They're only applicable for certain holds. From a stability perspective, again, at the design and approval stage, there will be a number of load cases made up and checked against the applicable rules and criteria, which will be shown in the stability booklet. These will make assumptions again about the state of the cargo, whether it's solid, how it, the weight of it, the density, but not necessarily that it's fully liquid. In general, I'd say bulk carriers have good stability. I mean, they're boxy ships. They're beamy, so unless there is issues with liquefied cargo, they generally have a good stability. So what can be done potentially to improve or mitigate some of the concerns from a liquefied cargo, both from a structural perspective and also stability? From a structural perspective, I guess it's relatively quite straightforward. Make things stronger, so change the assumptions from a design stage to actually consider what are the potential pressures or loads applied to the different structures, including when you get a liquid cargo. However, this obviously general will add more steel, so therefore makes it heavier and makes the ship less efficient. And especially nowadays, everyone is looking to make things more efficient. So there's a number of cons to doing that. From a stability perspective, operationally, there's a couple of points to consider. So trimming the cargo at the loading, so that is the case of not just leaving it in a big heap in the centre of the hold, but actually trying to spread it out so the top of the cargo's flat, move it into the corners of the hold to try and prevent any sliding. If it does want to start moving, then try and reduce that as far as possible. And then from a loading condition, try and make the stability of the vessel, the GM, neither too big or too small. Because if it's too small, you might roll too much, or if it's too big, you get high acceleration. So there's that kind of balance. From a design perspective, I guess there's only really one effective measure that can be done, and that is a more longitudinal subdivision. So instead of having holds that span the full width, then put in longitudinal bulkheads to break that up. This just shows an example of a typical bulk carrier on the left, where the hold, as I said before, side shell to side shell, but the ore carrier has big side, on the right has big side tanks, ballast tanks, because ore is quite dense. They don't need so much volume. They're more worried about it weight, so they don't need the full beam. So that's one potential. But then if you look at that, the cargo hold is far smaller, and if it becomes far less flexible in terms of the different types of cargo it could carry. Similarly with these, this examples of tanker vessels. So again, they are specifically designed for carriage of liquid, and you can see that they all have some kind of longitudinal subdivision to try and significantly reduce that resurface effect. Yeah, but again, that's more steel, increased light ship weight, less dead weight, so it affects the operational efficiency of the ship. some conclusions. So I guess the main, one of the big points is that when cargo liquefaction does happen, there is a real risk to the vessels that are carrying the cargo, shown to be deadly, and it can happen very quickly, instantaneous, without warning, giving the crew very little time to react. So there are regulations in place, the IMSPC code, and they do generally work when they're applied correctly and followed. They are constantly updated, so they do try and incorporate any latest developments in different cargoes, for instance, or different types of testing. So the typical bulk carrier design with its large hold is susceptible to cargo liquefaction, or potential design mitigations that could be done, although they shown to have some quite significant impacts on the operational profitability of the ships. So one possible design solution that may not be liked by shippers or ship owners is that cargoes that may liquefy, the Group A cargoes, the most dangerous, are only allowed to be carried on ships that are specifically designed for the carriage of that cargo, which incorporates some of the aspects that we've been through, whether that's from a stability perspective or increased strength.